come. I mean, there's only, I basically it's only whoever is available, right? I don't know where the rest are, right? Maybe they feel that they got better things to do than to go through the paper. But yeah, so I'm gonna go through with you now. So Lucas, this is Lucas' paper. So obviously he doesn't really need my help in a lot of things. He's just here for the show, which is very thankful for you, Lucas. Because I really only need, like, I really only do things when there's an audience. So even though, yeah, even though, like, most of this thing is like, you already know how to do already. But thanks for being here. So Wei En, I'm sorry to say, but since you're the only other audience here, a lot of the kind of like the, right, not that I'm targeting you, it's just that, like it will be directed at you lah, right? So I'll be asking you what are the questions you need me to go through, and based on what the other people message me, right, I'll go through their questions as well. Come, so start with you. Let me know which one you want me to go through. Okay, can I just double check with you? Your audio is a bit iffy. Are you using earpiece or are you outside or something like that? Oh, I see. Oh, ouch. That's tough. Okay, Ken. All right. Thanks for letting me know. So don't worry about it. I will then go through the thing. Okay. So you're using your phone, is it? Okay. Ken. Yeah. So I'm gonna do this one here. So you're asking me for question 3, right? Sorry, question 3. Oops. Okay, question 3. So I just couldn't hear it carefully. To understand question 3, hang on, let me just clear all this out first. To understand question 3, you basically have to go through B5, right? But like I said again, B5, I'm gonna send the video out. So yeah, but I'll just go through a very quick example with you. Let's start off with the basics first. Let's say I have 5 volts on one end and 5 volts on the other end, and I connect it with a wire, right? I hope you understand that there is no current. No current in the middle here. And why? Because there's no potential difference. No potential difference. That means the voltage is the same on both sides. Okay? Alright? So since the voltage is the same on both sides, then current will not flow. This also applies if you were to try to put 2 batteries next to each other. Hey Leo, did you message me for the questions? Okay. No, as in like is there any particular question you want me to go through? Because I'm using one of the scanned copies to go through this thing here. The first, oh, you're talking about structure, is it? Okay, Ken. Okay. So if anything, this is I'm going through question 3 MCQ first. All right. So very quickly, I just wanted to point out that, even if you, okay, we got people joining in now. Right, even if you have like 2 batteries, right, same voltage, right, on both sides, and I place them positive side to positive side, right, what would be the current inside the branch here, right? What is there any current inside here? Basically the answer is no current again, right? No current, right? So the idea of what you're doing here, even if you put ammeter will give you reading 0, right? The I equals to 0 amperes. Okay, so you put an ammeter there. Okay, there's no current. Why? Because the voltage, there's no potential difference again, no PD. Right? And what's the question asking for? What's the question asking for? So the question here, the question is asking you, like, what is the magnitude of P for the reading on the ammeter to be 0? You want the ammeter here to be 0. Okay, so that's the idea. You want it to be 0 amperes, right? It's the same concept. It's the same concept. So they ask you how many volts must P be in order for the ammeter to be 0, which means that how many volts is on the 3 ohm resistor. Okay. So to do this question, I mean, if you understand this picture, right? 5 volts, balanced 5 volts, no current in the middle. right? Then you translate it over here. What volts here? What is the volts here? So to do this question, what you need to do is you need to just ignore this branch first, like kind of like ignore this part here first, like don't care about this, right? Just understand that, right? Your job is to find out how much voltage is the 9 ohm and 3 ohm getting. So 24 volts, 9 ohm, 3 ohm. Now, if you have trouble trying to even figure out how many volts they have, you have to pay attention to the original lesson, right? You have to pay attention to the video, because otherwise, it's very hard for you to determine, right, to do the next part here. So it turns out that this, the student who did this, right, knew how to split the voltage. 24 volts split series 9 3 ohms, 18 volts goes to this, right, 6 volts goes to this, so it's 6 volts here. Okay, now knowing that the 3 ohm gets 6 volts, and I place the other battery here, the unknown battery here, over to here, and I want to get 0 amperes, right, it tells me that the battery here must be also 6 volts. Right, then it will be balanced, and once it's balanced, there's no current flowing, so the answer here is B. Okay, Ryan, are you okay so far on this? Okay, now this method of me explaining is kind of like a very summarized version of what actually goes on, right? This is to help you understand the question. This question, you're gonna get questions that are gonna come out differently next time, and if the questions comes out differently next time, right, it's gonna be again messy. It's gonna be like, if you don't have the fundamentals, so you have to make time to catch up on B5. This is circuitry B5 to if you want to get the full understanding of how this thing works, right? Like everything, all the other little nuances as well. Okay, so question 3 done. Is there any other things that you want me to go through for MCQ? 4? So 4 is something that everyone got wrong, right? Because this was a classic. Okay, that's why I say, right? That's why I say I have a very strong feeling that your this rotation of teachers, right? They're really very nasty. Okay, this question is one of the most controversial questions in IB physics, right? And yet they go and put it down here like this. Why? Because they want to show the students that they're not smart enough, or maybe they never study. But the problem is, even if you go online, you go onto Reddit, right? You can't find this thing anywhere. Like this thing doesn't even appear. Like not that there's a definite answer in Reddit, right? Everyone's complaining about this question, right? There's no answer anywhere. There's no real explanation anywhere. Okay, these people are horrible. Okay, so the idea here is that we know that for SHM, right? We know that for SHM, as the pendulum swings, the acceleration in the middle should be what, Lucas? It should be 0, right? Acceleration is 0, right? Why? Why should the acceleration be 0? Why? Excellent, right? So if you think about SHM, right? A equals to negative omega square x. Okay, A equals to negative omega square x. Okay, then the x is 0. When the displacement is 0, then A is 0 lah. And if A is 0, then the resultant force should be 0, right? Right or not? Okay? Okay, I agree with you guys. I totally agree with you guys. Okay? Right? I agree that this is correct. I think Reddit can't even figure this out, because the IB people, this didn't even appear on the examiner's report. Like nobody knows why. The answer is D. Okay, right? But like they didn't void this question, and they didn't say that in the examiner's report that there was something wrong with this question, right? Turns out, right, that the way I see it is that this pendulum right now is not SHM. For this particular question, is not SHM, right? Look at the clues. A simple pendulum oscillates as shown. What are you showing me? You're showing me A, B, C. If it's SHM, right? If it's SHM, it should have oscillated with a very, very small angle. such that the displacement is almost horizontal. However, in this picture, as you have shown me, it's an arc, which means this is closer to circular motion. Lucas, you want to curse and swear or not? I also. The worst is nobody online has explained this before. The examiner report also don't have. Okay? So if it's closer to circular motion, then the question is, okay, fine, if I treat it as circular motion, that means that you need to recognize that, right, the two forces acting on the pendulum bob as it passes through the equilibrium, if it's closer to circular motion, then that means T minus mg equals to mv squared over r, which means that it is not at equilibrium, right? There is not an equilibrium of forces when it's passing through the middle. The angle is too big. It is not small angle SHM. So, like that. This doesn't apply here. And therefore, okay, so the thing is this, the idea is there's never an actual value to it, Leo. I'm so sorry to tell you, but there's never an actual value to it. But students are supposed to understand that SHM, right, is when the displacement looks horizontal. The displacement must be completely horizontal. This one, however, is an arc, because this question says as shown. Right? like you feel like you want to throw something at someone, right? Of all the questions, I hope that they won't go and give this question. This is obviously trying to be nasty here. Whoever said this question is just a nasty person. Right? I'm gonna ask you this. Did they go through this question? What did they say? Correct. But because of this as shown, right, students are supposed to look at this diagram and realize that, oh, it's not a horizontal, it's not small angle approximation, it's not truly SHM, it's more of circular motion. And therefore, since it's circular motion, in the middle it's not equilibrium, there's a resultant force. And therefore resultant force is never zero. So the idea here is for pendulum, okay, strictly speaking is circular motion. Because you have a string, you have an object, and it's moving like that, it's swinging like that. Technically speaking, it's all the way circular motion. For pendulum, right, the SHM is an approximation, but you can only approximate it when the angle is small enough. And I know students are very concerned about what's the value of small enough. Right, I get that, but there is no answer to that. Right, it's only small enough when the pendulum's displacement looks almost horizontal. Then it can be considered as SHM. So he's not wrong to say that the pendulum is both circular motion and SHM. But to be very clear, it's baseline pendulum is circular motion, okay, when it oscillates. But we treat it as SHM when we have small angle displacement, and therefore the displacement is like almost horizontal like that. Then we can treat it like SHM. Okay, Leo? Yeah? Okay. So for this particular question, because they say as shown, we need to see it, we need to recognize that, oh, it's not very SHM-like, and therefore we will treat it as a circular, and therefore in the middle, there is a resultant force. It's freaking annoying, this question. Alright, but let me tell you this, okay? This only happened one time in the entire of IB. Only one time. Like, and of all the damn questions they can choose, they go and choose this one. Why? Because they want to prove a point. Right? They want to show students, oh, you all never study hard enough. Nobody explained this one. And this is a one-time, one-off question. How can you ask students to be able to do this think like, like, or understand it, like, like, oh, you never study hard enough kind of nonsense. This question is not. This question is very off-putting, to be honest, right? But every year I see ACSi teachers come up with these questions once, like, a few times. It's super annoying. Okay, anyway, so question 4 done. All right, next one, come. Next MCQ. Question 5, is it? A traveling wave of period 5 milliseconds travels along a stretched string at a speed of 40 meters per second. 2 points are 0.05 meters apart. What is the phase difference between the 2 points? Okay, good. Right, so we basically have a wave, right? We have a wave that's traveling along a string, right, like this, right? And they tell you that there are 2 points that happens to be 0. What? 0.05 meters apart, is it? 0.05 meters apart, and they ask you what's the phase difference between the two, is it? Okay, so we don't know what's the phase difference. I don't know what's the phase difference. Yeah. Okay. So since they give you the distance here, this is distance, right? Okay. And they want you to find phase difference, right? Do you understand if I tell you that phase difference can be calculated by the path difference divided by wavelength times 2 pi radians? Does this make sense to you? Path difference divided by wavelength times 2 pi radians. Leo? Okay, so do you understand what path difference is firstly? Okay, that's you using waves. I'm asking you about the two particles. Like, it's only one wave here. You're not wrong, you're correct. But for the context of this question, there's only one wave and there's two particles. So what does path difference mean for them? Correct, right? Like, how far are they away from each other, right? Okay, let me ask you this. Okay, how about this, Leo? How about I give you another example here? So I'm going to draw two blue dots. You see this blue dot here and that blue dot there? Okay, what's the path difference between the two of them? One wavelength. So if you take one wavelength divided by one wavelength and then you times 2 pi, what do you get? So what's the phase difference between these 2 points? Which is what? Are they in phase? Yeah, they're in phase, right? Yeah. So what you're doing here, what we're trying to do here is basically just need to find out what's the difference, right? Like, of their distance away from each other, divided by one wavelength, divided by one whole wavelength, as a fraction of how much they are different compared to the wavelength, like a fraction of a wavelength. Then I times 2 pi to give me my phase difference. But obviously what we don't have in the question is we don't have the wavelength, right? Yeah. We say what? What? Yeah. They gave us sorry, they give us the speed, right? The speed and the period, right? So you got to use that to find wavelength then. Right, so whoever, yeah, one of you guys, right, you found the wavelength over there, right? So 0.05 divided by the wavelength, then times 2 pi radians, that will be the phase difference. So I think the answer should be B. You get that now? Okay, hi Jay. Any questions you want me to go through? Jay? Okay, anyway. Any other questions? Wayan? Come on. Question 6. Let me take a look at 6. Question 6. Yeah, like that. Okay. Question 6. Wait. Where's the question? Oh, did they have a typo, guys? Was there a typo in the exam, and then you have to write in the question yourself? But I don't see the question. Like, yeah, correct. Where's the point of like you have to handwrite this question yourself? Yeah, what the hell? Okay, but yeah, the question is asking you where's the compression. Okay, so let me tell you this. Okay, so this thing here, I think I better send it to you via video, because the way to explain this is very lengthy, right? If I know that something I can explain very quickly here, I'll explain. But I know that my guys, I mean, all the regulars, they all know how to find the compression. I'm assuming they all know lah. Actually, I think I'm pretty sure, because I went through this quite in detail. So can you drop me a message to ask me for the compression stuff, right? How to find the compression, right? Yeah. So what you do is you make a list of what you need me to cover for you for the CT. So if, let's say for example, you don't know the B5, the circuitry stuff, right? The circuit stuff, right? Can you send me video for B5? Then after that, can you help me? Can you send me video to find compressions, right, and rarefactions on a wave, right? That sort of thing, right? Send it to me. Okay, right? As we go along, as in like, or you can compile it and give it to me later. Then you know, over the next few weeks, right, you can start catching up on those things. Okay, 7. Do I need to do 7? What happened to Jay? How come like he joined, then drop off, then join, then drop off? That means he is also doing online, right? Wait, you mean he still has training now at night? He's not done yet? Oh wow, okay, that's tough, man. Okay, that's fine then. All right. So he's like in the middle of his training somewhere. That's hard. Okay. Okay. What's the next question you guys want me to do? Come, tell me. Anything else from MCQ? Lucas, Wayan, Leo? Nothing from MCQ, Wayan? Okay, so I go into structured. Okay, structured questions. 11, anyone? Anyone? 11? Actually, I think even the group chat also, like, the people who are asking for questions also didn't ask much also. They also asked for the same, 13, 14, and 15. Right? Pretty much everyone asked for 13, 14, 15. 13A, 14, 13, 14. Okay lah. 12 Okay, 12. 12 is circuits again Okay. So maybe we found your Achilles heel, right? The thing that kind of like probably haunted you since secondary school actually, right? I tell you what, for 12, does Leo and Lucas need me to do 12? Can? That's alright, that's fine. Okay. Alright. So what you need to do is, okay, I'll go through this. I think someone else also got this wrong. Like I think it was towards the end of the lesson, she came up to me and asked me, I can't remember who, I think it's Emma. But I mean, I'm sorry, Emma, in case you're watching the recording later on. Okay, right. I'm hoping, okay, so if you don't understand the concept of internal resistance, please watch the video, right? That will be me explaining what internal resistance is. But for the most part, always treat internal resistance sort of like just another resistor in series, right? Sort of like another resistor in series. Okay. Leo, what was the question? The question asked you to find what? Find the internal resistance, is it? Okay, can, right? So the idea here is they kept the switch open first. They kept the switch open first. Essentially, what you have is a voltmeter connected to the battery. This is the battery, okay? This is the battery. And if you're not sure how the battery is actually looking like, the battery actually looks like this. Right, let me just draw the battery for you. The battery looks like this. This is like the battery, you know? Yeah, something like that. Right, the positive terminal is on this side, the negative terminal is on this side. The internal resistance is inside the battery itself, okay? And right now the switch S is open. So if switch S is open, right, you know what? We just ignore the bottom part. Like nothing's happening at the bottom part. So right now what we have is, right, a battery connected to a voltmeter. Okay, now this is a bit worrying sometimes, because at IB you need to recognize that some voltmeters may not be ideal. Okay, right, Leo, what does it mean to be an ideal voltmeter? Good. So we have to check the question. It did say there is an ideal voltmeter. What that means is that it's a resistance infinite voltmeter, right? Why is it so important for me to emphasize that? Oh, you know what? I need to check. Oh, ideal, right? Ideal means infinite resistance. Why is it so important? When the resistance is infinite for a voltmeter, no current can flow. The current does not flow at all, because it's infinite resistance. It's completely blocking the current. So no current can flow. And if no current can flow, then what you have is, right, if no current can flow, then what you have is whatever the reading of the voltmeter is, that is the exact EMF of the battery here. Because you notice that they didn't tell you what's the EMF. Okay, sorry, Leo, what was the voltmeter reading when the switch S was open? What did they say? What's that? Open is 12 volts, huh? Okay, sorry, let me just, guys, hang on, let me just check let me just check something first. I need to, oh, okay. All right, okay. So, we have this, okay? Yeah, 12 volts, is it? Let me just write this down, 12 volts, huh? 12 volts. So this actually informs me that the EMF of the battery is 12 volts. That means the original, right, whatever the EMF is 12 volts. It's like legit 12 volts, 12 volts, okay? All right. Then we go through the next question, the next part, right, where we close the switch. Okay, so when you close the switch, that means this bottom part here is in play now, right? So I erase it. Okay, the bottom part is in play now. So this one is connected to this one. It's a switch is closed, right? There's a resistor here, right, like that, right? It's still an ideal voltmeter, so current still doesn't flow through it. Okay, the current still doesn't flow through it. So now the question will be, right? Now the question, so the internal resistance is unknown. That's what we're trying to find, right? We're trying to find R. Right, we're trying to find R here, like this. R, that. Okay, what is the reading of the voltmeter now when the switch is closed? 8 volts. 8 volts, huh? 8 volts. Okay, 8 volts. Leo, were you here when I was teaching B5? Damn it. Yeah, you are. Okay, so right now the voltmeter, right, the voltmeter is reading 8 volts, okay, when the switch is closed. Okay, I'll tell you this, if you go back and review the video, I mean the original lesson I went through, do take note that the voltmeter is reading 8 volts. This is the voltage given to this resistor. When you're connected like this, right, this is also called the terminal PD, right? The terminals PD, like this. This is the voltage given to the external resistor. So technically speaking, this voltage here, right, the voltage given to the resistor there is 8 volts. Let me write this for you. This is 8 volts here. Do you understand this so far? Okay, what that means is that the internal resistance is getting 4 volts. The internal resistance is getting 4 volts. So the external resistance is getting 8 volts. The internal resistance is getting 4 volts. Okay, this is a very important part. I'm going to ask you a question. Like, if you don't remember this part, then you have to go and watch it. Let me ask you this, Leo. Can I put a voltmeter across and get a reading of 4 volts? You can't, right? Okay, so you remember this. Right, so if let's say I take another voltmeter and I place it over here like this, right? I place it across here like this, right? The reading of the voltmeter will not be 4 volts because 4 volts is inside the battery, right? You cannot possibly take out the internal resistance and find out what's the measurement of the voltage. The internal resistance is part of the battery. In fact, if you do put a voltmeter on the outside like this, right? This voltmeter also reads 8 volts. You get this, right, Leo? Okay, so 12 volts is the EMF of the battery. Okay, hang on. Okay, so I can sense where the mistake is really, right? Like where your misconception is. Okay, so knowing that this outside here is also 8 volts, maybe it is a good time for me to redraw the circuit a bit. Okay, so I'm going to redraw the circuit so that you can understand. It's not the fact that you have to do it, but I'm going to redraw it so that you can see it better, right? I'm going to draw it like that. So I'm going to draw the battery. The battery is a 12 volt battery, right? I have resistor R, big R here like this. This guy is 4 ohms, right? He's getting 8 volts. Then, right, the internal resistance, right? Okay, I said that you cannot bring it out, right? But since it's a diagram, I'm going to just bring it out. Okay, I'm just going to bring it out to the side here like this. Right, I just put it to the side here like this. Do you understand that the internal, this small little resistor gets 4 volts? You understand, right? But why? Very good. Okay, excellent. Okay, so you understand this part here. Okay, so do you understand that? Do you understand that if I put a voltmeter here to here, the reading of the voltmeter is confirmed 4 volts on, like legit on. Do you understand that? But do you understand that this is not possible? Like, this is impossible to connect it like that. Okay, you understand that? Good. So technically speaking, the only way to possibly connect a voltmeter is to connect onto this end and onto this end, which will show 8 volts, correct? From the part where the switch was open. Okay, good. Okay. No, you're absolutely right. Okay, anyway, hang on. I'll come back to that. Okay, so Leo's question is asking what happened to the internal resistance at the start again. So we go back to the start in just a while. But for now, since I've done it like that already, right? So very quickly, this is a 4 ohm resistor. It gets 8 volts. This internal resistor gets 4 volts. So how much must be the resistance of this internal resistance? It must be 2 ohms. Because voltage and resistance is proportional in series. When you're in series, right, the higher the resistance, the more voltage it gets, right? And it's by proportion. So if they say this guy gets 8 volts and this guy gets 4 volts, it means that the resistance here is half of the 4 volt, which means it's 2 ohms. Right? So do you understand this is 2 ohms now? That's the answer, right? Okay, good. Right. Now we come back to the original question. Leo was asking, how did they, again, what happened during the the first part? How did they get 12 volts? You know what, I apologize because I think I kind of like missed out on that. So I'm going to go through it very quickly now. Right, so back to this voltmeter again. Right, back to this voltmeter again. Okay, okay. So the understanding is, since there's no current flowing, right, no current flowing. Okay, so we write down here no current. Right, since there's no current flowing, the internal resistance is not in play, like what you said. Yeah, no current, right? No current means internal resistance. Internal resistance can't do anything, like it's not doing anything. It's only when current starts to flow, right, then the internal resistance will start to take up some voltage. You see that? When there's no current, internal resistance is not in play. So the voltmeter will legit read the full EMF of the battery. 12 volts here, 12 volts there. That's the thing here. So this guy here is like not in play because there's no current flowing. So if you want to write down a small little note on the side, you can write this down. You can say that internal resistance will take up voltage only when current is passing through it. If there's more current flowing, right, then the internal resistance will take up even more voltage. Okay? Okay, Ken. Right, so that's for number 12. Right, that's for number 12. This one here, is it this one here? Oh gosh. Wow, what's this, man? The minimum time. So this one is more like a energy power kind of question, right? Energy power kind of question. Should I go through this? Should I go through this question 12, this one here, this part here, 12B? If not, I'll go through 13 already. Okay? Leo, sorry, what were you saying? Okay, can. Right, then like that, I'll go through 13. Right, so if nobody asks for this one here. Actually, this one here is like quite annoying also because this one here is just the intensity is watts per meter square. You multiply by the area, you get the watts. You get the watts already. Then afterwards, you go and find out what's the power required. Right, they ask you to what's the minimum time, right? Because power is energy over time. Okay, so 13. Let's do 13. I believe the request was 13A, 13B. I got request for 13A. They ask you, outline why cylinder performs SHM. So it is very important that you remember SHM is what? SHM is, right? SHM is A equals to negative omega square X, right? In an equation, it means that A is directly proportional to X, A is opposite in direction to X, okay? So they're asking you, why does it perform SHM? It's asking you, right, can you prove that the equation is linked to this, right? Then some students get a bit stuck. But then SHM is A, acceleration, but then that's force, right? So what's the link between force and acceleration? Right, you divide by mass. So we can show that F over M equals to negative rho A GX over M, okay? And F over M, F equals to MA. And therefore A equals to negative rho big A GX over M. And therefore we can see, oh, yeah, right, it follows the same relationship. Acceleration is proportional to X and opposite in direction to X. Therefore, it's SHM. That will be your full answer there. That will be 13A. All right, so for those who are asking for 13A, that's the answer. I also got a request for 13B. Right, I'm also going to do 13B now. So 13B says, mass of the cylinder is 118 kg, cross-sectional area is 2.29 times 10 to the power of, what's that? Minus 1? Is that minus 1? Shoot, I can't see this shit. Oh, the minus 4, I think it's a minus 4. Minus 4. Density is this. Show that the angular frequency on the oscillation is what this. So it's like, oh, you know, technically speaking, what they're asking me to do is to use this equation to find omega. Because they want us to find angular frequency. They want us to find omega. That's what it is, right? So the trick to this question is to compare coefficients. Right, compare coefficients. So you can see this, rho AG over M is omega squared. So if you write this down, rho AG over M is omega squared, right? Then you square root the bugger over the side there, right? All the values are given to you. Everything G is 9.8. You can find omega from this, right? So for those who are asking for 13B, right? For those who are asking for 13B, this is how you calculate it. So maybe the people who are asking for 13B, you missed the point on how F and A are related, right? Maybe you missed that point there, like this, right? But I did mention many times before, don't forget, SHM, right? A equals to negative omega square X. Then you need to find the link, A versus F, right? Yeah. So this question here is, I'll tell you this question came up many times already in the IB, right? So I guess in a way, I apologize for not having put this into my my practices. Maybe you could have gotten it right, understood it. But yeah, you got to make the link, right? Not all questions you have been done before. Okay, so almost everyone who messaged me asking me for help wanted me to go through 14, so I'm going to go through 14. Okay, you know, we got to recognize this, right? So C3 is a horrible chapter. It is the biggest chapter in the whole of the IB physics, right? You have to go through two source, double slit, single slit, diffraction grating, standing waves later on in C4, right? Yeah, so the question is you need to figure out what scenario this is. One loudspeaker, two loudspeakers, equidistant from microphone, frequency and intensity are the same. They are in phase. A is in a fixed position. So what we have here is at the microphone right now is a constructive interference. Okay, it's a constructive interference. So let me zoom in now. Right, they're equidistant, you know. So what we have here is a maxima. Right, maxima for now. Right. So this distance x. This distance x is the same distance, path difference 0, phase difference 0. They are in phase difference 0. Constructive interference is a maxima. Let's check it out. Let's look at the graph. Okay, let's look at the graph. So at the start, initially, right, this is what we call initially. Let me circle the word initially. Initially. So the initially is here. This is the initially. Right. Then B starts to be moved further away from M along the line MP, right? It starts to move further away from M, right? Then the graph shows you the variation with distance, right? So as we start moving away, we start move away. What we notice is that the intensity here, right? This maximal intensity, right? This is the intensity, right? Intensity here, okay, is the graph here, the y-axis here. That's the intensity here. As we start moving B away, right, away, the graph starts to drop. The graph starts to drop, and it starts to drop to a point here like this. Okay? So, some students will be like, why is this graph not hitting 0? Why is it not hitting 0? Shouldn't it hit 0? Because I expect to see a minimum, right? But they are mistaken, because the idea here is that this is a minimum. You have to always remember, right? Like this is a minimum. You have to remember minimum doesn't mean 0 intensity. Minimum, right? Minimum means this is the smallest value you can get. So if let's say I move B backwards by a certain distance, let's say I move it by let's say a certain distance D, for example. And then it turns out to be a minimum, right? Down there like that, right? Okay, so when the source B, right, is here at a certain distance away, and it turns out to be a minimum now, right? Minimum, right, which is this one here. This tells me that the distance that I move back by, it just happened to be half a wavelength. Right? It's like, because how do I get a minimum? A minimum is when one wave and the other wave, they are different by half wavelengths. Half a wavelength, 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, and so on, right? But this is the first time. So as I move B backwards, this is the first time I get a minima. So this distance here, right? The distance at the bottom here, this one where my hand is pointing, that has to be half a wavelength. Okay, all right, that would have been half a wavelength. And I don't know whether you can accurately measure how much is that, but whatever the value is between 10 to 20, that's half a wavelength. Okay, then as you move further and further back, the intensity again goes up, right? The intensity again goes up. It's like, oh, it's increasing again. This is again another maxima. Okay, so it tells me that if you continue moving backwards, right? If you continue moving B backwards, right, at some point it becomes a maxima again. So why is it a maxima? Because this is now one wavelength away. Like the D plus the D would have been one wavelength. That means if you go and measure the whole distance here, right? You measure the whole distance from this point to this point here. That's one wavelength. That's one whole wavelength there. Okay? Yeah, but that's how it works. So as you continue moving back, right, it will dip again 1.5. As you continue moving back, it will rise again 2 wavelengths, right? As you move back again, right, like this. But there are some questions that some students may ask. Why is it that the pattern is not consistent? Why is it not like, why is it not going like, like a consistent pattern? Why is it getting less and less and less and less? Why is it like getting less, right? And the answer is this, okay? As you move it backwards, the intensity from B and the intensity from A is getting more different. Like B will become fainter. So you have a constant amplitude from A, but from B, right, the B's amplitude is getting lesser and lesser and lesser, which is why the maximas are getting lesser and lesser and lesser, right? Because it's no longer as constructive as it was before, right? Like, I mean, it's still constructive interference here, but it's less intensity interfere with the A's intensity. That's why the max is getting less and less and less. Okay, right? Yeah. So that's what's happening here. Some students have the very bad misconception thinking that, oh, this is a standing wave. So they call these nodes and antinodes or something like that. This is completely out, right? That means out of context already. That means your concept is completely off already. We are not talking about standing waves here. There's no standing waves, right? Some students get very confused because like, oh, like I thought that the sound from a speaker hit the wall, then there's a microphone, then, I thought it's the same as this case here. No, it's not, right? For standing waves, right, the two waves must be traveling opposite of each other. This is obviously not traveling opposite. This is going at one angle, and this one is going at the other angle. So, not standing waves at all, right? I say that because there was one year, one of the teachers went to tell the students that this was a node and antinode, and it confused the heck out of the students. So I had to tell the students to ignore whatever the teacher was saying. Okay, so explain why the received intensity varies between maximum and minimum values. That's exactly what I just said, right? Everything that I just said to you just now, that's the reason why it changes from maximum to minimum, right? As you move backwards, the path difference becomes half lambda, destructive interference. As you move further backwards, the path difference becomes 1 lambda, then it becomes constructive interference. So essentially, the idea here is this: as long as you move B backwards by, let's say the distance is equal to n lambda, that will be constructive interference. If you move the distance by n plus half lambda, right, equivalent to n plus half lambda, that will be destructive interference. So therefore, the intensity at the microphone, right, the received intensity at the microphone varies between maximum and minimum values as B is being moved backwards further and further back, right? That's your standard two-source interference. Okay, state and explain the wavelength of the sound measured at M. The wavelength would be, oh wow, what's the wavelength? The wavelength would be this, right? So I believe, I'm sorry, I have a scanned copy of this. I can't really see this very clearly, right? I can't see this very clearly, but it would seem that the wavelength is like what I mentioned to you here. This is one wavelength, right? Because that's when you get another maxima again. So that means the path difference is one wavelength. So this is the path difference, and therefore, right, it's one wavelength now. Okay, very good. All right, so there you go. Then they say B is placed at the first minimum. The frequency is then changed until the received intensity is again at a maximum. Show that the lowest frequency at which the intensity maximum can get is about 3 kilohertz, right? Okay, so for this particular question, lose the mark, lose the mark. Get your 38 upon 40. This is hard. Okay, I agree. This one is hard. So I'm going to go through it very quickly though, even though I say go ahead and lose a mark. But for me to do this, I need to clean up this shit here. Okay, there we go. All right. So this is a completely different scenario. I am now doing 14C, I believe. Right, I'm now doing 14C, so pay close attention to this. Okay, so that question there, let me just let me be very, very clear on this. It's placed at the first minimum. You see, this one also Gabra also, right? Right. Then you change the frequency until it becomes a maximum. Okay, can right? I can do that. Right. But hang on, is it both frequency are changed? Yeah, both frequency is changed. Right, both frequency are being changed. So I'm going to place B, right, at some distance, which is basically for the first minimum, that's half a wavelength. So according to the question just now, all right, according to the sample just now, right, this one here is I mean, the one wavelength is 26 cm, 26 cm as shown here like this. That's where the maxima is, 26 cm. So the first minimum, that means I place B 13 cm away, 13 cm away, right? And then they tell you that, okay, right, the frequency is now changed. The frequency is now changed. I will have a new frequency such that it's again a maxima here, right? Maxima here. So you know what? Okay, I think we can deal with this very quickly actually. In order to get a maxima, the 13 cm must now represent one wavelength, right? Or maybe or two wavelengths, okay? Right, I don't know, but I think it should be one wavelength. The most basic should be one wavelength, okay? Right, so the most basic should be one wavelength. So now we just need to find a new frequency. So since it's a new maxima, is now a maxima. Now a maxima, according to what the question says. Okay, look at the question. Let's go through the question again. Right, frequency is changed until the received frequency intensity is again a maximum. So I change the frequency, right? So I'm going to change the frequency such that the 13 cm is one wavelength. So lambda equals to 0.13 meters. V equals to F lambda. In the question just now, they tell us the V is 340. So 340 equals to F times 0.13. Right, F will be divided by 0.13. Right, so oh yo, why the number so off one? Okay, so the frequency is 26, according to my calculator, 2615 hertz, right? 2615 hertz. But the very strange thing is that the question says, show that it's about 3 kilo. Anyway, this guy is correct also, right? 2615, about 3 kilohertz. This is such an off value, right? So you're supposed to show, oh, that's about 3000 hertz. That's weird, right? They should just say about 2600. Yeah, okay. And then that was it for 14. Okay. It seems that there's also a request for 15. Okay, there's also a request for 15. All right, so I'm just going to go through 15 very quickly. All right, 15. Oh, 15. Oh, this is a whole 15. Oh, 15 here. Okay, so 15 very quickly. Two parallel slits. Wait, hang on. Now the request I have was actually 15D. Right, the person was asking for 15D, right, 15D. Does anybody need me to do 15 ABC? Those who are online? Wayan, Leo? I'm sorry, I know you guys must be tired, but yeah. You need C as well? Okay, all right, good. Okay, so C, okay. So for for 15 here is double slit. So I tell you what, what's happening here in 15 part C and part D, part C and part D, right, is modulation. Okay, this thing called modulation. All right, modulation. Okay, so technically speaking, you should refer to the modulation video, right? You should refer to the modulation video. But I tell you what, let me do this my way, so that then we can understand what's going on here, right? So I'll give you the full modulation video for sure. Please keep a list of it also. Please remember to text me for, can you send me the video for modulation, right? So this guy knows what's up, right? He knows what's going on, all right? So that's great. Sometimes I find teachers very funny one. Obviously, you know it's modulation, right? But the teacher purposely don't want to put the tick over here. They're going to put a tick over here, you know? They don't want to recognize that. Actually, I don't think your teachers refer to it as modulation. I think they say something else, man. They say that there's a single slit and double slit effect, right? Mixed together. They don't use the word modulation. So some teachers, they obviously see this, right? They know that you're getting help from outside. Because they don't want to admit that they don't want to use modulation. These people are funny, man. Okay, but never mind. Okay. What I'll do is I'll do it my way here. All right. Okay, very quickly, I want to show you, right? This is double slit. Okay, and I'm gonna copy and paste this thing. All right, I'm gonna copy and paste this thing here, right? And I'm going to do whatever that question was saying. Okay, so the question was saying that, okay, right, if you look at the question says the width of each slit is increased. That means I increase the width of the slit. Okay, so if you look back at this picture here, right, I had a double slit, then I had a double slit but thicker now. The slit is widened. Notice that the separation of the slits is still the same, right? I know you think that they're closer, but they're not actually closer, because if you measure the midlines, right, the midpoint lines, right, the midpoint lines of the slits, they're actually still the same separation. So small d is still the same. Small d is still the same, right? That's the symbol that we use, right? Small d. Okay. What's the difference in terms of like pattern? What's the difference in terms of pattern? So let me just drag this down here. Okay, what's the difference in terms of pattern? So if you look at this one here, right, narrow slits, the pattern will look like this, right? Narrow slits, the pattern will look like this. It will be like very even, right? Very even double slit pattern like this. This is the, right, this is your double slit pattern here. Sorry, I had to redraw it a bit. Okay, it's a bit wrong. Oh, it's getting lesser now. Sorry. Sorry, let me just get rid of this. Yeah, okay, there we go. It's a very even intensity pattern, right? Very even intensity pattern like this. Okay, that's what happens when you have narrow slits. And what we like when I was teaching this in the original lesson, I like to call this the ideal double slit pattern. Ideal. Then you go and thicken the slits, right? Then what's going to happen is that the pattern will look a bit different. Okay, the pattern will look a bit different. And in fact, because you widen the slits, one of the things that happens is that more lights goes through, and then what you have is this effect called modulation, where the fringes, right, they will remain the same positions as where they were, but they will seem to increase, they'll seem to decrease as you go along to the sides, like that. You'll start to have this, like, there's an up and then a down, like that. Okay, the pattern will look like this. Okay, and yes, the effect happens when you have the slits a bit too wide. That's what happens. Okay, the original pattern doesn't appear anymore. I just left it there for a guide, but in fact it's all gone, right? So the original, like, this is the actual pattern that you see now. Okay, and if you continue drawing to the sides, this double slit pattern, if you continue drawing to the sides, eventually at some point it actually disappears, right? It actually disappears, right? into a blank like that. Okay, all right. So if you follow the original lessons, right, modulation happens because there's a double slit pattern, but it seems to be covered by a single slit effect pattern, right? So the single slit effect envelope, they call it the envelope, right? If you have heard your teachers mention about it, right, they call it the envelope. If you didn't know what that was all about, that is the envelope pattern, right, down here, like this. So that dotted line is your envelope. Okay, long story short now, we are just going to show you the equations for both. The double slit equation is S equals to lambda D over small d. The single slit equation is X equals to lambda D over B. Okay, so it turns out that when you widen the slit, the single slit envelope starts to appear, and you need to recognize that X equals to lambda D over B. B is the slit width, which is this one here, the B, like, you know, how wide the slits are, right? The width of the slits down here, like this. Okay, I can zoom in. I know it's a bit small, but I'm going to zoom in now, right? This is the slit width, like this. So small d is slit separation, right? Small d is slit separation. Small b is slit width, like how wide the slit is. Okay, like that. And yeah, the idea for modulation mathematically, right? So all the math behind this is that you have to deal with both the calculations of S for the double slit and for the single slit. Let me be very clear about this, right? This is double slit. This is a double slit pattern. This equation belongs to the double slit pattern, the red color pattern. That's why I use red color, right? Red pattern. And then the blue one, the blue equation here, this one is for the single slit, right? The single slit envelope, right? So one of the peaks is missing because the single slit envelope goes in and then makes it disappear. It kind of like it interacts with this slit, and this slit becomes a minimum. If you watch the original lesson, then you will realize that for single slit, right, the two most important points is the central maxima as well as its first minima, which is here, right? If you watch the original lesson, right, the double slit pattern is the difference, is the peaks, right? This is the double slit pattern. I mean, this one here, the peak here, the peak here, the peak here. Okay? So S, what is S? S will be the distance from here to here. That's S. Okay? What is X? X for the single slit envelope will be from the center to the first minimum. Right? To the first minimum. Okay? Right? All the way to this point here, like this. That's X. Right? And your job is to use these two equations and do the calculations for whatever the question is. In this example that I'm showing you here, for example, right, you need to recognize, you need to be able to count. So X, right, how many S's, right, is X equals to, right? So 1, 2, 3, 4, 5, 6, 7, and then 8, right, which is the missing one. I mean, my drawing is not the best, right? 8 here. So X is equals to 8S. Right, so X is equals to 8 of the S's here, right? There you go, right? But it changes from question to question. So we look back at the question now, right? In case, because you see, right, this whoever set this paper, right? Whoever set this paper, they totally didn't provide a diagram at all, right? They didn't provide a diagram at all. They expected the students to understand what's modulation, right? They didn't even say it. They say, suggest after this change, the intensity at P will be less than that at M, right? Why? Okay, the answer is because there's modulation, right? There's a single slit envelope. Look at that, right? Single slit envelope. So it causes the intensity to dip to the sides, right? That's modulation there. Then it says, show that due to the single slit diffraction, the intensity at a point on the screen at a distance of 28 nm from is 0. Oh goodness, right? So single slit, right, at the distance here is 0. Right, so your job is to, right, come back to here, right, come back to the thing here, and then recognize that the distance that they want to ask you about is 28 mm, right, and all that. So your job is to combine these two equations to each other. Yeah, your job is to combine the two equations to each other. So let's look at the numbers given to you. Okay. Right, let's look at the numbers given to you. All right. Okay, firstly, the distance between the slits is 0.12 mm. 0.12 mm. Right, so as an example here, right? So I'm going to use given in the question. So they're telling you that D is equals to 0.12 mm, right? 0.12 mm, right? Then what were they saying just now? They were saying that B is, sorry, slit width is 0.03 mm, 0.03 mm, right? B is 0.03 mm, okay? Then essentially you are supposed to check X and S. So for this case here, for this example here, this thing here is like, you know, this thing here is like, we don't know how real this is. This is, you know, we're just using this graph as an example. Okay, so we fit in the numbers there, right? So S is equals to lambda D over 0.12 mm times 10 to the power minus 3. Sorry, I think I better put in the correct numbers. Then X is equals to lambda D over 0.03 times 10 to the power minus 3. Okay, that's in mm lah, right? Okay, your job, they wanted you to show what? They wanted you to show that due to single slit diffraction, the intensity at the point on the screen at the distance of 28 mm is 0. They are talking about this point here. The intensity is 0. They want you to show that the X is equal to 28 mm. Okay? Right? So the other information that you need is what was S? How much was the distance between the two bright fringes? So we go back to this thing here, right? Did they provide any information about the distance? Wait, did they? Oh, wait. What's P? P is the first maximum of intensity, and they gave you distance MP, 7 mm. So that means that the distance here, this is S, and S is equal to 7 mm. There we go. So now we know S is 7 mm, right? Right. Back onto my diagram here, what they're saying is that the distance between this peak, right, one of the double slit peaks, and the other double slit peak, that was 7 mm, right? 7 mm. It was already 7 mm from before. This is already 7 mm, right, as before, right? This 7 mm. Okay, so that means that this is 7 mm equals to lambda D over 0.12 times 10 to the power minus 3, and this is X equals to lambda D over 0.03 times 10 to the power minus 3. Right, you're supposed to combine these two equations, right? And I think you can tell, 12 divided by 0.03, 12 divided by 3, sorry, 12 divided by 3 is like 4. 4 times of 7, right? X is equals to 7 times 4 equals to 28 mm. Okay? Will? Understand? Yeah, this is tough, okay? I think the easy part is the calculations. Right? The easy part is to understand the like, you know, to look at the calculations. Basically, I'm combining the double slit and single slit equations into one. Right? That's what I'm doing. That's the easy part. The hard part is what in the world was going on, like, you know, how, like, why was it happening? What do you mean by intensity is 0? How come? Right? So that means you have to go back and look at the what do you call it, the modulation, right, lesson that I taught before. Okay, we good? I mean, I'm done here, guys. Like that was it for this the whole paper already. That was the last question, right? Yeah. So if modulation, if modulation is something that you need help in, please drop me a message, ask me for modulation. Otherwise, I am done. Any other questions, Wayan? No, okay, can. Right, then I will see you guys when I see you guys, whenever that is. Please remember that the next lesson will be me finishing B2 and starting on B3. Right, I should be able to finish syllabus quite soon. Okay, bye-bye guys. Bye-bye. Thanks, Lucas. Thank you, Wayan. Bye-bye.